Before I proceed to harmonic oscillator problem further, let me discuss for a few moments the canonical commutation relations. For example, Heisenberg uncertainty principle is a canonical commutation relation. This is equation 1, which tells us about the canonical commutation relation of position xi xj. Suppose you can take this as x and y, you can take this as y and z, you can take this as x or z. So positions within themselves commute, momentum components within themselves also commute. This is px, this is py, suppose. But for position and momentum, if this is x and this is px, if this is y and this is px, what will be the commutation relation for that? The general commutation relation for xi pj is ih cross delta ij. If I and j are different, using the property of Kronecker delta, we can say that they commute. For example, if this is x and this is py, which means I and j are different, so delta ij becomes 0, which means x and py commute. X of that is the x component of position and y component of momentum will commute. But if I equal to j, that is if this is y and this is py, this commutation relation becomes ih cross. This is the fundamental commutation relations as described by Paul Dirac. Paul Dirac also observed that the commutation relations in quantum mechanics can be obtained from classical relations just by replacing the classical Poisson bracket by the commutators. If this is classically the Poisson bracket of two variables to function, in quantum mechanics this becomes commutation relation of the same variables divided by ih cross. This is equation 2. For two functions q and p, the classical Poisson bracket by definition can be written like this. Suppose a is a function of both q and p, b is a function of both q and p. This is classical Poisson bracket relation. By definition, this can be written like this, where s can take any value 1, 2, 3. I mean, if we are in 3 dimensions, so it's 1, 2, 3. From the general rule of partial derivatives, I need to write this as del A del Q, because A is function of both Q and P. If A is function of only one variable, I will write it as dA dQ. In classical mechanics, the Poisson bracket relation of momentum and position is this one. This is equation 4. But in quantum mechanics, the canonical commutation relation, we call this as canonical commutation relation, is given by equation 5. And let me tell you about some relations. We need to actually memorize the canonical commutation relations from 6 to 11